The first stimulant we will be going over is Adderall. Adderall is typically used to treat ADHD and narcolepsy. However, many people may abuse this drug as it causes them to focus better and to perform at a higher level. So here's how the biology works. Dopamine is a neurotransmitter in the brain, represented by the black dots, that is associated with reward, happiness, and pleasure. Dopamine is transported through the cell by little gaps or pockets called vesicles. When an electrical signal is transmitted, those gaps move through the cell and their contents are released through exocytosis at the end of the cell. From there, they enter the synapses. This is a little space in between two cells. On the start of the other cell are neuron receptors. Dopamine will bind with these receptors and continue the signal of pleasure, reward, and happiness throughout the brain. Once the signal is done being transmitted, dopamine goes back into the cell through reuptake channels, so it's ready to go again the next time the signal is transmitted. However, when Adderall comes into play, the drug goes through the reuptake channels and occupies vesicles that dopamine normally would, resulting in excess dopamine in the synapses. This causes the brain to relay the signal of reward over and over again, causing a very high feeling. Now, how can Adderall go through the reuptake channels that are only designed for dopamine? Well, this is because the two chemical structures are very similar. Now, the only real difference between dopamine and Adderall is the hydroxide that has been added to the end of dopamine and the CH3 that has been added to Adderall. Because Adderall and dopamine are almost exactly the same, this allows Adderall to go through the dopamine channels and replace dopamine, allowing you to become addicted to Adderall. So, what causes this addiction? Gradually, with continued use of Adderall, the body naturally lowers the amount of dopamine produced in the brain. So, over time, it will take more Adderall to provide the same effect. This leads to Adderall dependence and ultimately to Adderall withdrawal. The physical withdrawal symptoms of Adderall are fatigue and insomnia. So, how do we stop this? Well, in order to understand the process of addiction, we have to first understand the chemicals and everything involved at a molecular level. First, let's start with the parts of the atom. In an atom, we have protons, electrons, and neutrons. Protons are positively charged, electrons are negatively charged, and neutrons have no charge. Protons and electrons are attracted to each other. In Adderall, we have carbon, nitrogen, and hydrogen. Here's how to identify the parts of an atom using the periodic table. First, we have the atomic number. This shows how many protons the atom has and what defines it from all the other atoms. Next, we have the element abbreviation. This is what the element is called. And third, we have the atom's mass. So, the next question to ask is, how do carbon, nitrogen, and hydrogen attach to make something such as Adderall? Well, the answer is intramolecular forces. The first intramolecular force I'll be talking about is ionic bonding. In ionic bonding, one atom has a strong electronegativity, meaning that it really wants an extra electron to fill its valence, and another atom will have a very low electronegativity and will really want it to get rid of its extra electron. So, the atom that really wants an electron will steal the electron away from the atom that wants to give it up, and one will have a negative charge and one will have a positive charge. The next type of bonding is metallic bonding. In metallic bonding, the electrons flow freely throughout the nucleuses, meaning the protons and neutrons of the atom, and just kind of float around in a sea of electrons and nucleuses. There's no real structure to this other than that nucleuses form rigid structures that we know as metals. The final type of bonding, and the type of bonding that is used in Adderall, is called covalent bonding. In covalent bonding, two atoms will share an electron in order to reach the capacity of their valence orbitals. So, what happens when we get a bunch of molecules or atoms that have been covalently, ionically, or metallically bonded in one place? Well, this is called intermolecular forces, and this includes dipole-dipole forces, hydrogen bonding, and London dispersion. First is dipole-dipole forces. In dipole-dipole forces, molecules become what we call polar. Now, what is polarity? Well, water is polar. What happens in water is that oxygen is covalently bonded to two hydrogens, and oxygen has a valence electron of 6 and it wants to reach 8, and hydrogen has a valence of 1 and it wants to reach 2. So what happens is these two atoms, or these three atoms, form two bonds, and since oxygen is more electronegative than the two hydrogen, the electrons will tend to stay more around the oxygen atom, and so the oxygen atom gains a negative charge, and the two hydrogen atoms gain a positive charge, making this uneven electron that is now what we call polar. Next is hydrogen bonding. Hydrogen bonding is basically an exaggerated version of dipole-dipole forces. It formed by a covalent bond with a hydrogen. Now, since hydrogen has only one atom, it will easily get rid of that atom and create very polar molecules. Finally is London dispersion. Now, London dispersion is kind of tricky since you wouldn't think of electrons to be close to one another since they had the same charge and would repel each other. But electrons don't actually spin in orbits around the nucleus. They kind of dart in and out of space and time, and so it is possible for them to dart at the same time in the same area and become close to another. So what happens once that occurs is one side of the molecule has those electrons, and so it becomes negatively charged, and the other side of the atom becomes positively charged. This creates a weak force between molecules that is the weakest force on intermolecular forces, and can even cause noble gases which don't have any electronegativity to become slightly polar. So these intermolecular forces are what cause molecules to become attracted to one another and ultimately form the states of matter. Now, the states of matter are typically thought to be solids, liquids, and gases, but actually there's a few other ones which I won't get to today. But weak attractions such as London dispersion and dipole-dipole forces will form gases at room temperature, but stronger forces such as hydrogen bonding and even covalent bonding, which is crystalline structures, will form liquids and solids respectively. In neurons and synapses, there are mostly aqueous solutions. An aqueous solution is any molecules dissolved in water. One example of this is cerebrospinal fluid, which is the fluid that's in the brain. This is what lies in between the synapses. Our entire body is made up of mostly aqueous solutions. Now, back to molecules. Now, you may be wondering, how do molecules such as carbon dioxide get their names? Well, let's look at the example carbon dioxide. Carbon dioxide has one carbon and two oxygens. So let's break this down. The word carbon represents the one carbon in the molecule, and di meaning two, and oxide meaning oxygen. When it comes to naming, molecules are named by the number of a specific atom they have. For one atom, you would call it mono. For two, di. For three, tri. For four, tetra. However, in organic nomenclature, they have a different system. Organic molecules are named after how many carbons they have. For example, if they have one carbon, it's meth, two carbons is eth, three carbons is pro, and four carbons is bute. Now that we know how to name molecules and atoms, the question comes up, do these atoms and molecules ever disappear? Well, according to the law of conservation of mass, the answer is no. Atoms can go from atom to atom, and molecules can go from molecule to molecule, and any other combination, but they can never be created or destroyed. They can also change states. Molecules and atoms can go from gas to liquids to solids, or vice versa. They change, but they never disappear. Okay, now that we understand all that chemistry, it's time to move on. So, let's look at addiction. Once a person is addicted over continuous use of Adderall, the dopamine levels in their brain start to go down. So, in order to find a solution to the dopamine deficiency, we have to look closer at dopamine, as possibly the increase of dopamine production would lessen the harmful side effects of withdrawal. So, let's see what dopamine is made from. Dopamine is made from tyrosine, which then goes to L-dopa, which then is in turn formed to dopamine. Each one of these two reactions is catalyzed by an enzyme. So, let's look at the enzyme tyrosine hydroxylase. Well, first we have to understand how enzymes work. Enzymes work by speeding up the reaction rates of molecules. To do this, they lower the activation energy in order to start a reaction. To start a reaction, there needs to be energy. This energy that is needed to start a reaction is called activation energy. An enzyme, through a variety of mechanisms, lowers this activation energy. The way the enzyme tyrosine hydroxylase lowers the activation energy is using Fe2+, oxygen molecules, and BH4 to hydroxylate tyrosine. Now let's zoom in on BH4. Boron has 3 valence electrons, and each of the 4 hydrogen has 1. The hydrogen atoms want to get to 2, and the boron atom wants to get to 8. But wait, 3 plus 4 is only 7, and boron wants to get to 8. So how are these bonds possible? Well, in order to understand this, let's look at the rules for bonding. Electrons come in pairs, one with a negative spin and one with a positive spin. Contrary to popular belief, atoms do not actually spin in orbits, but rather in geometric shapes. These shapes are known as S, P, D, and F. S is what we know as a sphere. P is kind of drawn like a figure 8, F, 2 figure 8s, and D is frankly all over the place. Electrons fill up these patterns as demonstrated. Boron's electrons fill up until P2 and on the x-axis. Just the upspin. I could see boron trying to get 5 more to fill up all the P's, or getting rid of 1 to eliminate 1 P, or getting rid of 3 to eliminate both the P and the S. But 4? Now that's just odd. And there's really no way to explain this. Scientists have not yet figured it out. Anyways, let's get back to the next enzyme. The next enzyme is dopa decarboxylase. This enzyme lowers the activation energy, breaks the chemical bonds, and the bonds are reformed at the lowest energy state possible. So, now that we know how dopamine is produced, let's look back to the concept of the drug. If scientists actually made a drug that would increase the amount of dopamine produced, then wouldn't people become dependent on the drug that eases the withdrawal, and in turn had to go on withdraw from that drug? So, all in all, more research needs to be conducted on how to artificially produce more dopamine in the brain, so that possibly there could be an answer to how to ease withdrawal.